Hello, everyone, and welcome to this episode. Today, we're going to be answering just a small number of questions about AP Chemistry Section 3.3, which is entitled Solids, Liquids, and Gases. And to me, it's a short little section because it's kind of bridging a gap that we have between intermolecular forces and solids in our first two sections, and then three straight sections on gases. So this is just some kind of introductory background information about solids, liquids, and gases. Okay, so here's a quick question, and we have to be able to think back to maybe a particular diagram in our heads of what solids and liquids and gases look like. In a solid, all of the atoms and ions and molecules, whatever is there, are packed together in an orderly arrangement and they're not moving past each other. So we have a situation with low molecular movement, low kinetic energy, and a lot of rigidity. And then in the liquid phase, they break free from each other and they start moving around past each other into the liquid phase, and they would take the shape of their container. And in the gas phase, molecules are just flying around independent of each other and with a lot of space in the middle between them. Okay, so let's take a look at some questions, and this again will be kind of a shorter episode, I believe. Of the following, the best explanation for the fact that most gases are easily compressed is that the molecules in a gas, they can be compressed because, let's see, they're in constant motion, relatively far apart, have relatively small masses, have real non-zero volumes. Okay, I got to tell you that pretty much all four of these are true, but only one of them really answers the question. Yes, all molecules are in constant motion. They're flying around like crazy. They have relatively small masses. Most gases do. They have a real non-zero volume. That's true. They're not zero volume. They're a little bit there. But here it is in letter B. They are relatively far apart. So you're able to compress them because there's lots of space. So you can smush the container and still get the same number of particles in there. And so that would be the correct answer for that question. All right. Here's another longer one. We'll try to keep it short. PCl3 decomposes into PCl3 and PCl5. Forgive me. And there's the reaction. It's a decomposition reaction. And there's a bunch of information here. The initial pressure of the PCl5 is 1 atmosphere. The temperature is held constant until it reaches equilibrium with its decomposition products. The figures below show the initial and equilibrium conditions of the system. So maybe you've studied equilibrium before, maybe you haven't. That's not as important here. And this would be also included in the equilibrium unit. But the idea here is that over here we have one gas and it's at 1 atmosphere of pressure. Over here we have 3 gases because the reaction produced 2 more gases from the one that was there. And so we have more gas in this one and the pressure went up. Which of the following is the most likely cause for the increase in pressure observed in the container as the reaction reaches equilibrium? And the choices are a decrease in the strength of intermolecular attractions. That's not going to be right because intermolecular attractions for a given set of molecules are going to be the same at all times. The only difference is how much kinetic energy they have to allow those intermolecular forces to play with each other. So that'll stay the same. An increase in the strength of intermolecular forces? Nope, that's also the same. An increase in the number of molecules, which increases the frequency of collisions with the walls of the container. That sounds pretty good. Let's check D. An increase in the speed of the molecules that then collide with the walls of the container with greater force. So we might end up with a situation where the speed of the molecules increases, but that would be accompanied by a corresponding increase in temperature. Temperature is a measure of average kinetic energy. So if the temperature had changed, we could talk about molecules changing average speed, which leaves us with letter C as our correct answer there. All right, the next one has a couple of parts to it. For parts of this free response question that require calculations, clearly show the method used and the steps involved. So we're going to do that. So dry air, we're talking about dry air here, is comprised of nitrogen, oxygen, and traces of other gases. A student obtains 2-liter container filled with a sample of dry air at a total pressure of 1.3 atmospheres and a temperature of 295 Kelvin. calculate the total number of moles of gas in the container. In order to do this one, we have to look at what we have. We have a 2-liter container, that's a volume. We have a pressure and a temperature, and it says calculate the number of moles. So if you have learned your gas laws already, then you know that this is an ideal gas law question where PV equals nRT, and we're going to solve for N. P is pressure, V is volume, T is temperature. So the pressure we're going to substitute in is 1.30 atmospheres. The volume is 2.00 liters. The number of moles is something we don't know. But because we need an ideal gas constant, and because we're in atmospheres, I'm going to use the one given in atmospheres, which is 0.0821 liters, atmospheres, moles, kelvins. And the temperature is 295 Kelvin. So thankfully, they gave it to us in kelvins and not Celsius, which saves us another unit conversion. So always have to have Kelvin temperatures in gas laws. And finally, if we solve for everything, 0.107 moles of air. Okay, so 2 quick things. Number 1, I always say this, if you're using a formula, make sure to write down the formula. Then substitute in with units on everything that gets a unit, and then solve and put your answer with a unit at the end. Now, you might be thinking, well, hey, Mr. Rudolph, does this even work? Because we have a mixture of gases. It's got nitrogen and oxygen. Don't I have to treat them separately? And it's getting too confusing. But one thing that we have to learn is that under the same conditions, pretty much all molecules of any gas behave identically if we're assuming that they're ideal gases. In this case, we are. So if the particle is a little heavier, it'll move a little slower. If it's a little lighter, it'll move a little faster. But overall, its pressure and its volume and those things tend to stay even with each other and consistent from gas to gas. So we can just treat the mixture as one gas. That's all we can do. And so there's that. Now, last 2 quick questions. The student cools the gaseous mixture until either nitrogen or oxygen condenses. Which gas will condense first? Justify your answer in terms of the types and relative strengths of intermolecular forces. And then, using the legend given, draw at least 3 molecules of each type of gas in the sealed container, represented below when one of the substances has condensed but the other substance is still a gas. This is going to be our pause the video moment for this episode. Since we've already done intermolecular forces and we've done some particle drawings, take a moment, see if you can answer both of those 2 questions, sketch a little particle drawing, and see you in a couple seconds. And if you were able to, for letter B, predict that O2 is going to condense first, as you cool them down, O2 is going to condense first, happens to be at like minus 183 degrees Celsius. Because it has a more polarizable electron cloud, it has 1 more electron per atom than nitrogen does, and therefore a higher London dispersion force. So you don't have to get it quite as cold before they start sticking together into the liquid state. And in your drawing, you need to be able to draw the O2s down here at the bottom, because liquids will settle to the bottom of the container and hang out there, taking the shape of their container, while the gas is still in the gas phase above it. And so something like this, I drew 4 molecules of each. You might have done just 3 or 5 or something like that. But a diagram something like that would work. All right, I hope you found this helpful. This is AP Chemistry section 3.3. If you have any questions, send them to me in the comments. And in the meantime, happy studying and have a great day.